Okay, today it turned out that we show this identity obtained probability current, but now we have to we have to determine another expression. So it's our day to do integrals. We'll be more or less done with it today. Okay, so the next thing that we want to do is we want to discuss momentum. So up to this point, we have just looked at the position, probability, etc., such things associated with the particle, but we have not discussed its momentum. Now we see that this probability density tends to move around, so that means the particle is moving around. And the way we are going to identify momentum in this theory, at least using this methodology, is to say that, okay, let me define some expected value of momentum, and that is going to be mass times the change in the average position of the particle. Okay, so that sort of makes sense. The particle on the average is moving along the x-axis, and at certain points, okay, we know how the we know how the average position is changing. So that's something like velocity. If I multiply it with mass, I get something like momentum. But since this is an average value, I also say this is the average value of momentum. Okay, it's difficult to identify momentum directly from the wave function because parts of the wave function are moving with different velocities, right? This j of x is different for different parts of the wave function. Okay, so in fact, let me just leave this as an exercise to you. If I have psi equal to this, our favorite wave function, Gaussian x over x0 squared plus I k0x, okay, just find what j of x is. Okay, simple algebra, but now you'll see that this wave function is actually moving. Okay, but not all parts will be moving with the same amount of current. So, in fact, it will be deformed and everything. But it's not easy. So, if I have this wave function like this at a certain time and it has gone to something like this, apparently different parts of the wave function are moving with different velocities. So I cannot just associate a single momentum with a wave function like this. So all I can do at this stage is to look at it on the average, saying that, well, on the average it was initially here, now it's there, so it must be moving with that velocity on the average. Okay? So let's look at that. Okay, so I'm going to get m dt of average value of x, which is going to be x times psi star psi dx. And now I integrate from minus infinity to plus infinity. I'll assume that this is a nice normalizable wave function. Okay? All right. So what happens? I am going to get this same sort of stuff again. So m minus infinity to infinity, two terms, x del psi star del t times psi plus del psi del t times psi star dx. Okay, we do the same thing that we did for the previous problem. We use the Schrödinger equation to analyze how these things are changing. Okay, so let me just remind myself. Del psi del t is 1 over I h bar minus h bar squared over 2m del squared del x squared psi plus v psi. That's our Schrödinger equation. And psi del psi star del t, okay, is equal to complex conjugate minus 1 over I h bar, okay, minus h bar squared over 2m del squared del x squared psi star plus v psi star. Okay, so these things we wrote earlier, but now I need them again.
Yeah, I think there is a minus.
Yes, there's a minus sign here, which is very important. Okay. Maybe at this point, let me open a parenthesis and discuss something, because this minus sign came up. Okay, so this is something on the side, not directly related to what we are doing, but it's interesting. In classical mechanics, we have what is known as time reversal symmetry, right? So what is time reversal symmetry? If we just reverse the direction of time and reverse the direction of all the momenta, etc., the equations are still the same. Okay, so in classical mechanics, right, we have dx dt, let me multiply it by m, is equal to p, and then I have d p dt is equal to f, okay, whatever, let me put it. Okay, let me do it in 3 dimensions, doesn't really matter. Okay, something like this. Now, what happens if I take t going to minus t and p going to minus p? Okay, so what am I doing? I'm reversing the direction of time, but I'm also reversing the direction of everything that's moving. Okay, so I'm really undoing whatever I'm doing. So under those conditions, I am going to get, you see, this t goes to minus t, so I'm going to get minus m dr d minus t is equal to minus p, because I changed the direction of p also. And I also have d minus p, okay, d minus t is equal to f. But if I cancel the minuses, okay, oops, there's no minus here. If I just cancel the minuses in all of these equations, I get exactly the same equations. Okay, so in classical mechanics, we have this time reversal symmetry. Do I have the same thing in quantum mechanics? Well, looking at this equation, you see this is what happens in normal, ordinary forward time. Now, if I look at this equation and change the direction of t, make that a minus t, it brings a minus sign here. So the way to cancel that is look at the complex conjugate psi. So if you take t going to minus t and psi going to complex conjugate psi, you again get the same equation. Okay, so in forward direction in time, you have psi evolving. In the opposite direction in time, it's the same equation except that it's psi star. Okay, so psi star represents the time reversed wave function. So we still have time reversal symmetry in quantum mechanics because psi and psi star basically are two wave functions which are just related to one another by a complex conjugate. Okay? Yes?
Can you explain why we didn't include x in the derivative?
X is a variable. It's not a function of time. Okay? X is just this axis here. Okay, so I have some psi of x and t. Okay, so these are independent variables. X and t are independent variables. X is what's happening in the position space. Okay, so x is not a function of time. Average value of x is a function of time. But x itself is an independent variable. Two independent variables, x and t. Okay, so in fact, this partial derivative here just says that inside psi, there's also an x. Don't differentiate that x with respect to t, because you would get 0 anyway, but just differentiate t. Okay? Yes?
Is it the same if we include special relativity into the picture? Or?
Special relativity comes in a somewhat different and non-trivial way. Okay? For those of you who are interested in what special relativity does to quantum mechanics, I recommend that you Google something like Dirac equation. Okay, Dirac equation, his name will come up again and again in quantum mechanics. And there are nice descriptions. Maybe I'll put a link in the web page because a few people are asking relativistic versions of this. Okay, you'll see that there is a nice, very beautiful, but unfortunately somewhat more complicated discussion of what happens when you put special relativity into this. Okay, so it's not directly applicable at this stage. Okay. Other questions? Yes.
For calculating the momentum, why don't we take the expectation value of the derivative?
Expectation value of the derivative?
Yes.
How would that? Okay, no, that would just give us 0, right? That's just what we discussed. If you look at something like dx dt, or partial derivative, this is just 0 because these are independent variables. X and t are the independent variables here. We have functions here of x and t. So this is a function of x and t, which are two independent variables. And the derivative of one with respect to other is 0. These are just two independent variables. Okay, so we cannot use that, right? So x is just these numbers on the x-axis. They are not changing, okay? They are not moving in space. So we cannot do anything about that. Other questions? Okay, so let's now write this down. Okay, so we'll go through this algebra again. It is a little bit tedious, but we have to do it. That's life. Okay, so minus infinity to infinity, x. All right, let me put psi first. Psi star, so it's going to be 1 over minus I h bar. Okay, all that stuff, minus h bar squared over 2m del squared del x squared psi star plus v psi star. That's the first term. Then I have plus psi star over here, 1 over I h bar minus h bar squared over 2m del squared del x squared psi plus v psi. Okay, and everything integrated over x. Again, you see there's this term here, which is x times psi star times v. Same term here, psi star times x v psi, right? So they are the same terms. One of them comes with a factor minus 1 over I h bar. The other one comes in plus 1 over I h bar. So they cancel. So at least again, those terms are not there. Okay? Now, we are going to do what we did. In fact, it's already on the board. But we are going to, this is a different integral because it has an x in it. Okay? So we have to go over this again. Okay. When I was a student, I would get very mad if the instructor just changed the previous equation by making this plus, minus, etc. But now it's my turn to do it on you, but I'll not do it. Okay, I'll be a nice guy. Okay, so expectation value of P is equal to m minus infinity to infinity. Okay, I'll do exactly the same thing. I'll get, okay, well, del x of, okay, let's see. Let me factor some stuff out. So, if those v's cancel, you see the m's cancel also. And I can cancel one of the h bars. So I can pull out an I and a 1 over 2. Okay, so it's going to be h bar over 2I. Okay, check my algebra, I'll make mistakes. So, x times psi del psi star del x. Okay, so that's this term. Let's make sure the signs and everything are correct. H bar over 2I. Okay, x psi psi. Okay, very good. And then I have the same thing with the minus sign, which goes like x psi star del psi del x. Okay. Let me change the brackets because I want a bigger bracket. I want an even bigger bracket outside. All right. So this is the first term, del del x. Okay, and eventually there will be a somewhere over here dx. So again, is this correct? I cancelled that m. Okay, this m and that m. Okay. Okay, so this obviously is not correct because in the first equation I had derivative only, okay, acting on these derivatives so that I have second derivatives. So this is going to generate some spurious terms which I want to remove. Okay, so there will be derivatives on this term, on the psi's, and derivatives, of course, on the x's. So let me take them out. So minus, there's going to be x del psi del x del psi star del x minus x del psi star del x del psi del x. Okay, so I don't want that, right? But that's nice because really this term is equal to that term, so that's 0 anyway, just like the previous case that we did. But I still have one more term here. Okay, and that term is the derivative on x, so that's going to give me, okay, psi del psi star del x, okay, minus psi star del psi del x. Okay, now everything is correct. Yes?
What happens to the h's? There are h squared on one side.
H bars?
Yeah.
Okay, the h bars are cancelled. Okay, I had this 1 over I h bar,
Yeah.
and so I have,
But that's squared.
okay, so that remaining h bar I
Oh, okay.
pulled out. Okay, so, okay, but please do check my algebra. Okay, even if I confidently tell you that this is correct, there may be mistakes. Okay, my confidence is not an indication of correctness. All right, so I now have these two terms remaining. So this term is just 0 and disappears. This term, as we discussed last time, is the integral of a derivative. So what that will give me is that when I do the integral, it's going to give me just that bracket at plus infinity and minus infinity. But I have assumed that this is a nice normalizable function, so psi goes to 0 at plus or minus infinity. So that is also 0. And what I end up with is just only this last term. So let me just write that down. It's going to be h bar over 2i. Okay. And I'm going to get psi star del psi del x minus psi del psi star del x dx. Okay? Minus infinity to infinity. Now, if you look at this expression, this is again a complex number minus its complex conjugate. So it's going to be purely imaginary. And when I divide it by I, it's going to be real. Okay? Which is nice. Okay, that's a check on our algebra because we are trying to calculate this average value of P, and mass times the change in the average position of the particle, which is a real quantity. So there's no way I should get a complex result out of this. Okay, so this has to be something real. So it is nice to make these checks as you go along, okay, in the exam, etc. If I ask you what the expectation value of the position is, and if you tell me it's 5i or something, okay, that's something that should alarm you, right? An imaginary position, yes.
I understand, but why it should be real? I understand.
Okay, because it's the average position, average value of x, which is a real quantity, right? Average value of x has to be real. So its time derivative is going to be real, mass is real, so it's got to be real. Sure, yes.
Why did we say 0 first part?
Why did we say 0? Okay, because this is just this bracket evaluated at plus infinity and minus infinity. Okay, and these things go to 0 at infinities. Okay, both the derivative and also, of course, x doesn't go, but x times psi always also goes to 0. At least that's what we assume. Okay, yes.
Why was this number imaginary? Because it is the...
Okay, this is not imaginary because this is some complex number minus its complex conjugate.
Okay.
So this piece is imaginary.
Okay.
Divided by I is real. Okay, so I'm okay. All right. Now, I have two terms here. Let me just look at the second term. Yes.
Even though we know wave function goes to 0,
Yes.
but we are multiplied by x.
X. Well, we assume that x times psi star psi also goes to 0. Okay? Because what does that mean? If x times psi star psi is even just constant, that means psi is going to 0 like the square root of 1 over square root of x, right? So that would mean psi star psi goes down like 1 over x, which it diverges. Okay? Do you follow that argument? Okay, so if x times psi star psi, okay, I am interested in what is happening to this as it approaches infinity. Obviously, it could diverge or go to 0, but I have to make sure that psi star psi itself is converging. Okay, so the worst thing that this could do, so I don't want this thing to grow up exponentially or anything, because otherwise I would not be able to normalize it. So the best thing that this can do is the total product can go like a constant. Okay, I'll give it an exclamation mark, question mark. Okay, when would it go like a constant? If this psi would go down like 1 over square root of x, then of course psi star and psi would both go down like 1 over square root of x. Then it would be constant and I would worry about it. But then, if that's the case, then you see this psi star psi would go down like 1 over x, and that diverges. Okay, so that cannot be normalized. So if psi star psi is normalizable, it has to go down faster than 1 over x. And if it goes down faster than 1 over x, then this has to go to 0. Okay, so we are safe. All right, so let's look at the second term. Second term is minus psi del psi star del x dx. Now, in quantum mechanics, whenever we have these nice convergent wave functions, we can do an integration by parts immediately. Okay, so I can immediately write this as integral, lose the minus sign, del psi del x psi star dx. Okay, why is that? Because again, if we want to do this one more time, so let me put a question mark. Why can I do this? Well, I can always write this as minus integral, again, del x of psi times psi star, but I'm making a mistake, right? So I have to correct that mistake by putting in this del psi del x times psi star. Okay, all of that. Okay, I have to remove that dx. This is 0 at the limits, same argument. So I end up with this equation. Okay, so this is very convenient actually. Always remember this. Whenever we have a normalizable wave function, in fact, the two things do not have to be the same wave function as long as they are both wave functions. So that if you have a function f here and the g there, you can always convert it into, okay, g and f. Okay, all right. So again, in the more general case would be if I have two wave functions minus f del g del x dx, I can always write this as plus g del f del x dx. Okay, it's just integration by parts. There's no contribution from the infinities, and it's a very useful relation whenever you are making calculations. Okay? Yes?
Shouldn't we also subtract del psi star over del x times psi?
Let me see. Did I? No? Okay. I think it's okay. Okay, so what this means is if I just add this with the minus sign, with these things interchanged, it becomes exactly the same thing. So I'm going to get, okay, I lose the 2, h bar over I, psi star del psi del x dx. Okay, now we'll write this in this following form. We'll write this as psi star h bar over I del x psi dx. Okay, so let me write the left-hand side also and put this in a box. Okay, so this is the expectation value of momentum. Now, why did I put those terms in together? Well, just remember that when we have the average value of x, which is going to be psi star x psi dx, I put this x in the center just so that it looks like that one. That is the expectation value of x, and that is the expectation value of p, yes.
So we define momentum as operator?
Yes, so this object here we define as the momentum operator, the capital P, and this is then the expectation value of this operator P. We are going to generalize everything from classical mechanics. Okay, so if you like, this is a postulate of quantum mechanics. In classical mechanics, you can express all dynamical quantities in terms of position in one dimension x and also px. Obviously, if you have 3 dimensions, you also have y, py, and z, pz. And what happens is that the same thing goes over to quantum mechanics, as an operator. Okay, so the x operator in this case is simple, it just goes to x. But the p operator, the px operator, goes to h bar over I del x. Okay, so this is now our px operator. So we cannot talk about definite quantities as in classical mechanics, but we can talk about their averages. So the average of x is just the expectation value of x, as we have written here. If we have x squared, the only thing I need to do is square this. Similarly, if I want to find the average value of p squared, I'll just need to square that. So whatever function of x and p I have, x and px, okay, that's going to go into x, the same function, f of x and h bar over I del x. Okay. So let's see how we're doing. Okay, we still have some time. As an example, for example, what is the z component of the angular momentum in classical mechanics? Yes? L is r cross p. Okay.
X times py minus
Okay.
y times px.
Y minus px. Okay, so this is the angular momentum operator in classical mechanics. In quantum mechanics, it's going to be x h bar over I del y minus y times h bar over I del x. Okay, so obviously angular momentum cannot be defined in one dimension. You have to go into these x, y, z coordinates. Okay, so that's what happens. So everything that you have in classical mechanics, we just carry into quantum mechanics, either with the x or the coordinates themselves, or these px, py, etc. in that form. Okay? Okay, any questions? Okay, we don't have much time. Well, we still have something. Yes. Yes, very good. An important point. So let me pass this to the back again. It will come back to me. Okay, thank you. All right. So finally, we can return back to our problem here. I need this. Okay, but okay, that's okay. In any case, maybe we can do without it. All right, so let's move over here. I was hoping to get the p squared out of this also, but we'll see. Okay, so let's see. So again, that's just as an example. Let's return back to our psi, which was equal to some a normalization e to the minus x squared over x0 squared plus I k0 x. So this is our wave function at a certain time. Okay, we have not put down the time dependence to it, but we can, because we know the psi, we can determine what the expectation value of momentum is. So that is going to be equal to, okay, psi star del x, there will be an h bar over I in front, psi dx. So it's going to be h bar over I, psi star, okay, minus infinity to infinity, psi star, which is going to be a star e to the minus x squared over x0 squared minus complex conjugate I k0x. What does the derivative with respect to x do to this function? It brings down an I k0. Otherwise, it's still the exponential. A e to the minus x squared over x0 squared plus I k0x. Okay, dx. Again, the phases
So
cancel.
we also must have minus 2x over x0 square. Because
Oh, yes, thank you. Very important. Okay, so let me put it in the back here. So the derivative is going to be I k0 minus 2x over x0 squared dx, right? So that's there. All right, but now you see this term with x here. First of all, just due to symmetry, it's equal to 0, right? And also, it's real, okay? Well, in any case, that's not... Okay, so this... I'm trying to rush things, so it's not good. So this is going to be h bar over I. I'm going to get minus infinity to infinity. This psi star psi part is still there. But then I have I k0 minus 2x over x0 squared dx. So this I k0 is just a constant, and the wave function is normalized. So I'm going to get h bar I k0 over I from the first integral. What is the second integral? Integral of x times psi star psi. 0, right? That's just the average position of the particle, and we decided last time that it was 0. Okay, so I get h bar k0. So that is the expectation value of the momentum. So that's the first time that we see k0 coming out in an average. So it didn't influence where the particle was. It didn't influence the uncertainty in the position of the particle. But apparently, it is involved in momentum. Okay, so this particle has an average momentum of h bar times k0. So this oscillation in the phase is making up the wave part of the motion. Okay, so I have something like a wave. Remember, if I had just this piece, it would be a free particle, but it is confined to a space near the origin. But still, this is indicating the average momentum of the particle as it moves. Okay, if we want to calculate p squared, let me just write down the equation. That's what we'll start with next time. Average value of p squared is going to be equal to psi star p squared, which is h bar over I del x squared psi dx. Okay, so this is now the momentum operator squared. So we'll find the expectation value of that, and we'll see what the, for example, uncertainty in momentum is. All right, any last minute questions? Okay, I'll see you Monday, right?